Shortly before night, he stepped on the plane at the Dallas airport, a tall, thin, balding man of 35, dressed entirely in black. Black shirt, black trousers, black socks, black sneakers. "Ah, Dr. Malcolm," Hammond said, smiling with forced graciousness. Malcolm grinned. "Hello, John. Yes, I'm afraid your old nemesis is here." Malcolm shook hands with everyone, saying quickly, "Ian Malcolm, how do you do? I do maths." He struck Grant as being more amused by the outing than anything else. Certainly Grant recognized his name. Ian Malcolm was one of the most famous of the new generation of mathematicians who are openly interested in how the real world works. These scholars broke with a cloistered tradition of mathematics in several important ways. For one thing, they used computers constantly, a practice traditional mathematicians frowned on. For another, they worked almost exclusively with nonlinear equations in the emerging field called chaos theory. For a third, they appeared to care that their mathematics described something that actually existed in the real world. And finally, as if to emphasize their emergence from academia into the world, they dressed and spoke with what one senior mathematician called a deplorable excess of personality. In fact, they often behaved like rock stars. Malcolm sat in one of the padded chairs. The stewardess asked him if he wanted a drink. He said, "Diet Coke, shaken, not stirred." Humid Dallas air drifted through the open door. Ellie said, "Isn't it a little warm for black?" "You're extremely pretty, Dr. Sadler," he said. "I could look at your legs all day, but no, as a matter of fact, black is an excellent color for heat. If you remember your black body radiation, black is actually best in heat, efficient radiation. In any case, I wear only two colors, black and gray." Ellie was staring at him, her mouth open. "These colors are appropriate for any occasion," Malcolm continued. "And they go well together. Should I mistakenly put on a pair of gray socks with my black trousers?" "But don't you find it boring to wear only two colors?" "Not at all. I find it liberating. I believe my life has value, and I don't want to waste it thinking about clothing," Malcolm said. "I don't want to think about what I will wear in the morning. Truly, can you imagine anything more boring than fashion? Professional sports, perhaps. Grown men swatting little balls, while the rest of the world pays money to applaud. But, on the whole, I find fashion even more tedious than sports." "Dr. Malcolm," Hammond explained, "is a man of strong opinions." "And mad as a hatter," Malcolm said cheerfully. "But you must admit, these are non-trivial issues. We live in a world of frightful givens. It is given that you will behave like this, given that you will care about that. No one thinks about the givens. Isn't it amazing? In the information society, nobody thinks. We expect to banish paper, but we actually banished thought." Hammond turned to Gennaro and raised his hands. "You invited him." "And a lucky thing, too," Malcolm said, "because it sounds as if you have a serious problem." "We have no problem," Hammond said quickly. "I always maintained this island would be unworkable," Malcolm said. "I predicted it from the beginning." He reached into a soft leather briefcase. "And I trust by now that we all know what the eventual outcome is going to be. You're going to have to shut this thing down." "Shut it down?" Hammond stood angrily. "This is ridiculous." Malcolm shrugged, indifferent to Hammond's outburst. "I've brought copies of my original paper for you to look at," he said. "The original consultancy paper I did for InGen. The mathematics are a bit sticky, but I can walk you through it." "Are you leaving now?" "I have some phone calls to make," Hammond said, and went into the adjoining cabin. "Well, it's a long flight," Malcolm said to the others. "At least my paper will give you something to do." The plane flew through the night. Grant knew that Ian Malcolm had his share of detractors, and he could understand why some found his style too abrasive, and his applications of chaos theory too glib. Grant thumbed through the papers, glancing at the equations. Gennaro said, "Your papers conclude that Hammond's Island is bound to fail?" "Correct." "Because of chaos theory?" "Correct. To be more precise, because of the behavior of the system in phase space." Gennaro tossed the paper aside and said, "Can you explain this in English?" "Surely," Malcolm said. "Let's see where we have to start. You know what a nonlinear equation is?" "No." "Strange attractors?" "No." "All right," Malcolm said. "Let's go back to the beginning." He He paused, staring at the ceiling. Physics has had great success at describing certain kinds of behavior. Planets in orbit, spacecraft going to the moon, pendulums and springs and rolling balls, that sort of thing. The regular movement of objects. These are described by what are called linear equations, and mathematicians can solve those equations easily. We've been doing it for hundreds of years. Okay, Gennaro said. But there's another kind of behavior, which physics handles badly. For example, anything to do with turbulence, water coming out of a spout, air moving over an airplane wing, weather, blood flowing through the heart. Turbulent events are described by nonlinear equations. They're hard to solve. In fact, they're usually impossible to solve. So physics has never understood this whole class of events until about 10 years ago. The new theory that describes them is called chaos theory. Chaos theory originally grew out of attempts to make computer models of weather in the 1960s. Weather is a big, complicated system, namely the Earth's atmosphere, as it interacts with the land of the sun. The behavior of this big, complicated system always defied understanding, so naturally we couldn't predict weather. But what the early researchers learned from computer models was that even if you could understand it, you still couldn't predict it. Weather prediction is absolutely impossible. The reason is that the behavior of the system is sensitively dependent on initial conditions. You lost me, Gennaro said. If I use a cannon to fire a shell of a certain weight, at a certain speed, and a certain angle of inclination, and if I then fire a second shell with almost the same weight, speed, and angle, what will happen? The two shells will land at almost the same spot. Right, Malcolm said. That's linear dynamics. Okay, but if I have a weather system that I start up with a certain temperature and a certain wind speed and a certain humidity, and if I then repeat it with almost the same temperature, wind, and humidity, the second system will not behave almost the same. It'll wander off and rapidly become very different from the first. Thunderstorms instead of sunshine. That's nonlinear dynamics. They are sensitive to initial conditions. Tiny differences become amplified. I think I see, Gennaro said. The shorthand is the butterfly effect. A butterfly flaps its wings in China, and weather in New York is different. So chaos is all just random and unpredictable, Gennaro said. Is that it? No, Malcolm said. We actually find hidden regularities within the complex variety of a system's behavior. That's why chaos has now become a very broad theory that's used to study everything, from the stock market to rioting crowds to brain waves during epilepsy. Any sort of complex system where there is confusion and unpredictability, we can find an underlying order. Okay? Okay, Gennaro said. But what is this underlying order? It's essentially characterized by the movement of the system within phase space, Malcolm said. Jesus, Gennaro said. All I want to know is why you think Hammond's Island can't work. I understand, Malcolm said. I'll get there. Chaos theory says two things. First, that complex systems like weather have an underlying order. Second, the reverse of that simple systems can produce complex behavior. For example, pool balls. You hit a pool ball and it starts to come off the sides of the table. In theory, that's a fairly simple system, almost a Newtonian system, since you can know the force impacted to the ball and the mass of the ball, and you can calculate the angles at which it will strike the walls. You can predict the future behavior of the ball. In theory, you could predict the behavior of the ball far into the future, as it keeps bouncing from side to side. You could predict where it will end up in 3 hours from now, in theory. Okay, Gennaro nodded. But in fact, Malcolm said, it turns out you can't predict more than a few seconds into the future, because almost immediately, very small effects, imperfections in the surface of the ball, tiny indentations in the wood of the table start to make a difference, and it doesn't take long before they overpower your careful calculations. So it turns out that this simple system of a pool ball on a table has unpredictable behavior. Okay, and Hammond's project, Malcolm said, is another apparently simple system, animals within a zoo environment, that will eventually show unpredictable behavior. You know this because of theory, Malcolm said. But hadn't you better see the island to see what he's actually done? No, That is quite unnecessary. The details don't matter. Theory tells me that the island will quickly proceed to behave in unpredictable fashion. And you're confident of your theory. Oh yes, Malcolm said, totally confident. He sat back in the chair. There is a problem with that island. It is an accident, waiting to happen.